September 15, 1944. Rabaul, New Britain. 0930 hours. Commander Takeo Shibata, 43, Chief Aviation Engineer for the Imperial Japanese Navy's 11th Air Fleet, approached the wrecked Corsair with measuring instruments and notepad. American forces had abandoned Rabaul, bypassed rather than invaded, leaving Japanese garrison isolated. But wreckage from air battles littered the area. This particular F4U Corsair had crashed 3 months earlier. Pilot recovered by American forces, aircraft left behind. Shibata's mission was technical analysis. Extract the engine if possible. Measure components. Understand design. Japan desperately needed insights into American aviation technology. The Corsair dominated Pacific skies. Understanding why might help Japanese designers close the performance gap. What Shibata found when he examined the Pratt and Whitney R2800 double Wasp engine would fundamentally alter his understanding of aviation engineering, not because the design was revolutionary in concept, but because the execution revealed industrial capabilities Japan couldn't approach. 2,000 horsepower. From an air-cooled radial engine, Japanese engineers had theorized such power was possible, but seeing it, measuring it, understanding how Americans achieved it, that was different. That revealed the gap between theory and industrial reality. By September 1944, the air war in the Pacific had turned decisively against Japan. American fighters consistently outperformed Japanese aircraft in speed, climb, and firepower. The F4U Corsair represented perhaps the most dominant American carrier fighter. In combat against Japanese fighters, Corsairs achieved kill ratios exceeding 10-to-1. Japanese pilots feared encountering them. Aircraft performance derives from the power-to-weight ratio. More power for a given weight creates better performance. The F4U Corsair's Pratt and Whitney R2800-8 engine produced 2,000 horsepower at takeoff power. Later variants produced over 2,400 horsepower with water injection. The engine weighed 2,350 pounds. This created a power-to-weight ratio of 0.85 horsepower per pound, extraordinary for 1944 technology. Japanese radial engines serving similar roles produced significantly less power. The Nakajima Homare 21, powering the Kawanishi N1K2 Sheidenkai fighter, was Japan's most powerful operational radial engine in 1944. It produced 1,990 horsepower at takeoff, nominally comparable to the R2800. But Japanese horsepower ratings measured under ideal conditions rarely achieved in operational service. Effective operational power was approximately 1,800 horsepower. The engine weighed 1,870 pounds, creating power-to-weight ratio of 0.96 horsepower per pound, seemingly better than the R2800. But those numbers hid critical differences. The Homare was notoriously unreliable. Overheating was common. Cylinder failures occurred frequently. Operational availability was approximately 60%, meaning 4 out of 10 Homare engines were non-operational at any given time due to maintenance issues. The R2800 achieved operational availability exceeding 90%. Reliability mattered more than peak power when aircraft needed to complete missions and return safely. Commander Shibata's examination of the crashed Corsair's R2800 revealed engineering details Japanese industry struggled to replicate. The engine was an 18-cylinder twin-row radial. Each cylinder had a displacement of 155.4 cubic inches, creating total displacement of 2,804 cubic inches. The cylinders were arranged in 2 rows of 9, staggered so each cylinder received adequate cooling airflow. The engineering precision was extraordinary. Shibata measured cylinder bore at 5.75 inches, with tolerances within 0.01 inches. Piston stroke was 6.0 inches with comparable precision. These tight tolerances were maintained across all 18 cylinders. Japanese manufacturing in 1944 struggled to maintain such precision consistently. Cylinder bore variations of 0.005 inches were common in Japanese engines, creating uneven power output and vibration. The supercharger was mechanically sophisticated. A 2-stage, 2-speed supercharger compressed intake air, allowing the engine to maintain sea-level power up to 21,000 feet. Japanese supercharger technology was less advanced. Most Japanese engines used single-stage superchargers, losing power rapidly above 15,000 feet. This gave American fighters decisive advantage at altitude where most Pacific air combat occurred. Materials analysis revealed another disparity. The R2800 used high-nickel alloy steel in critical components. Valve seats were stellite, a cobalt-chrome tungsten alloy with exceptional heat resistance. Pistons were aluminum alloy with steel reinforcing bands. These materials allowed the engine to operate reliably at high power settings and temperatures. Japanese materials couldn't withstand. Japan faced critical shortages of alloying elements. Nickel was scarce, chromium was limited, cobalt was unavailable. Japanese engine designers worked around these limitations using lower-grade materials and conservative power settings. But this approach guaranteed Japanese engines would be heavier and less powerful than American engines using superior materials. Commander Shibata's technical report, dated September 28, 1944, forwarded to the Ministry of Munitions and Naval General Staff, provided detailed analysis with sobering conclusions. The Pratt and Whitney R2800 represents aviation engine development beyond our current industrial capacity to replicate. Power output of 2,000 horsepower from air-cooled radial engine of this size requires precision manufacturing, advanced materials, and sophisticated supercharging we cannot achieve with available resources. Our analysis indicates three fundamental barriers preventing Japanese development of comparable engines. The report detailed these barriers. First, precision manufacturing. American production facilities achieved dimensional tolerances. Japanese facilities couldn't match consistently. This wasn't lack of skilled workers but lack of machine tools with sufficient precision. American machine tool industry was generations ahead of Japanese capabilities. Closing this gap required years of industrial development Japan didn't have. Second, materials. The R2800 incorporated dozens of specialized alloys unavailable to Japanese industry. Even if design specifications were copied exactly, Japanese engines built with available materials would be significantly less reliable and powerful. Material science capability gap was potentially wider than design gap. Third, production capacity. The R2800 was produced in quantities exceeding 125,000 units during the war. This volume production required industrial infrastructure and supply chains Japanese industry couldn't replicate. Japanese high-performance engine production never exceeded 20,000 units annually across all engine types. American production scale created quality advantages through refined processes and experienced workforce. The report concluded, matching American engine performance requires industrial transformation beyond current wartime capabilities. Our best approach is optimizing designs achievable with available resources rather than attempting to replicate American engines we lack capacity to produce. This conclusion reflected broader reality Japanese military leadership struggled to accept. Japan's industrial base, while advanced for an Asian nation, was 2 generations behind American industrial capacity. Steel production, machine tools, electrical generation, chemical processing. Every industrial measure showed similar gaps. These gaps translated directly to military equipment performance disparities. The human impact of engine performance gaps appeared in pilot experiences. Lieutenant Saburo Sakai, who survived the war as Japan's third highest scoring ace, described engaging Corsairs in his 1957 memoir. The Corsair was a formidable opponent unlike earlier American fighters. It was faster than our Zero. It climbed better. It dove faster. The only advantage we had was maneuverability at low speed. But Corsair pilots learned not to fight us slow. They used speed and power. Attack from above, dive through our formation, zoom climb away before we could respond. Our engines couldn't match their climb rate. We couldn't chase them up. We couldn't run from them down. They controlled every engagement. Skill mattered less when aircraft performance gap was so large. Sakai's experience was typical. Japanese pilots increasingly avoided combat with Corsairs when possible. Orders directed pilots to attack bombers and avoid fighters, but avoiding fighters that were faster, climbed better, and had longer range was impossible. Corsairs hunted Japanese aircraft with impunity. The psychological impact on Japanese aviators was severe. Pilots depend on confidence in equipment. When pilots believe their aircraft can compete, morale remains high. When pilots know they fly inferior aircraft against superior opponents, morale collapses regardless of training or determination. By late 1944, Japanese pilots understood they were outmatched. Some fought with desperate courage. Many became increasingly reluctant to engage. Unit effectiveness declined, regardless of tactical competence. Japanese aviation industry attempted to close the engine performance gap through the Nakajima Homar and Mitsubishi HA-43 programs. Both engines aimed for 2,000 horsepower output, using Japanese materials and manufacturing techniques. Both programs struggled with reliability problems stemming from inadequate materials and inconsistent manufacturing quality. Neither engine achieved combat effectiveness comparable to the R-2800. Post-war analysis revealed the industrial capacity disparity underlying engine performance gaps. American aviation engine production during World War II exceeded 800,000 units. Japanese production was approximately 90,000 units. The 9-to-1 production ratio reflected not just assembly capacity, but entire industrial support infrastructure. American factories had precision machine tools, skilled workforce, quality materials, and effective supply chains. Japanese factories struggled with all four elements simultaneously. The R-2800's success influenced post-war aviation development globally. The engine design principles, manufacturing techniques, and materials science lessons shaped jet engine development in the 1950s. Engineers who worked on the R-2800 program transferred to jet engine programs, bringing expertise in high-temperature materials, precision manufacturing, and reliability engineering. Today, the F4U Corsair is remembered as one of World War II's finest fighters. But the aircraft's success derived fundamentally from its engine. The airframe, though well-designed, was essentially a structure built around the R-2800's power. Without that engine's 2,000 horsepower, the Corsair would have been mediocre. With it, the Corsair was dominant. At the National Naval Aviation Museum in Pensacola, Florida, a cutaway R-2800 engine is displayed showing internal components. Visitors can see the 18 cylinders, dual magnetos, two-stage supercharger, and intricate valve train. Museum guides emphasize that this engine wasn't just powerful, it was reliable. During World War II, R-2800 engines achieved operational reliability exceeding any other high-power aircraft engine globally, a museum placard. Quotes a Navy maintenance officer from 1945. "We maintained Corsairs in forward areas with minimal facilities and still achieved 85% operational availability. The R-2800 was nearly soldier-proof. Follow basic maintenance procedures, and it ran reliably. Compare this to our earlier aircraft requiring constant attention to keep operational. The R-2800 meant more aircraft flying more missions with less maintenance. That reliability advantage multiplied combat effectiveness beyond what power output alone would suggest. The lesson extends beyond aviation. Technology advantages derive from entire industrial ecosystem, not just individual designs. The R-2800 was excellent design, but its excellence was enabled by American precision manufacturing, materials science, and industrial infrastructure. Japanese engineers could understand the design. They could even copy it, but they couldn't replicate it without the industrial base supporting it. This pattern appears repeatedly in technology competition. The visible product represents final output of extensive industrial capabilities. Competitors focusing only on the visible product miss the invisible capabilities that create it. Japan focused on aircraft and engine designs, attempting to copy or match them. But matching designs without matching industrial capabilities produced inferior results, regardless of designer skill. Commander Shibata understood this when he examined that crashed Corsair's engine. His report documented technical details meticulously. But his conclusions were strategic. Japan couldn't match American aviation engine development without industrial transformation, requiring years. In September 1944, Japan didn't have years. The war would be decided with existing capabilities, and existing capabilities were grossly inadequate. 2,000 horsepower. That number represented more than engine output. It represented American industrial capacity, materials science, precision manufacturing, and decades of aviation engine development expertise. When Japanese engineers examined captured R-2800 engines, they weren't just seeing a powerful engine. They were seeing the entire industrial civilization that produced it. A civilization operating on scale and sophistication Japan couldn't match. In aerial combat, that 2,000 horsepower gave Corsair pilots confidence their aircraft could outperform any Japanese fighter. It gave them speed to control engagements, power to climb away from danger, and reliability to complete missions, knowing their engine would bring them home. For Japanese pilots facing Corsairs, that 2,000 horsepower meant fighting opponents with permanent performance advantage they couldn't overcome through skill or determination. By war's end, over 12,000 Corsairs had been produced. They served through Korea and into the 1960s with some air forces. The R-2800 engine served even longer, powering various aircraft into the 1970s. Few aircraft engines have shown such longevity. The design excellence combined with manufacturing quality created an engine that remained competitive for decades. When Commander Shibata completed his analysis of that crashed Corsair's engine, he knew Japan had lost the aviation technology race, not because Japanese engineers lacked skill or knowledge, but because Japanese industry lacked capabilities to translate knowledge into hardware matching American capabilities. 2,000 horsepower wasn't just a number, it was a verdict.